You know, we've all seen those movies, right? Spaceships banking hard through asteroid fields, engines blazing. But what if I told you that real space travel is less about flashy dogfights and way more about, well, falling? Today, we're going to pull back the curtain and look at the hidden physics that actually makes these incredible journeys possible.
I mean, really think about that for a second. There's no air to push against, no road to follow, there isn't even an up or a down. So how in the world does this tiny metal box, hurtling along at thousands of kilometers an hour, make a turn in the absolute middle of nowhere? Well, the answer isn't about brute force. It's about a beautifully choreographed dance with the universe itself. So first things first, let's just forget everything Hollywood ever taught us. Real space travel is quiet. For like 99% of its journey, a spacecraft's main engines are totally off. It's this silent ballet, a game of cosmic billiards where you coast for years at a time and use entire planets to slingshot you towards where you need to go. Now, every single journey to the stars starts with the exact same colossal challenge: just getting away from Earth. This is, by far, the most energy-intensive part of any mission. It's a raw, violent display of power, all just to overcome the relentless pull of our own planet. That first hurdle, it has a name: escape velocity. And this isn't just about going up, it's about going out so incredibly fast that gravity literally can't pull you back down. It's the speed of no return. It's your ticket to the rest of the solar system.
And here's that magic number, 11.2 kilometers per second. That is so fast, you could get from New York to Los Angeles in under 7 minutes. It's just an insane amount of energy, unleashed in the first few minutes of flight, all just to earn the right to leave.
So, how do you actually push forward when there's nothing to push against? It's a super common misconception that rockets need air. But in reality, it all just boils down to Newton's third law. The rocket throws a massive amount of hot gas out its back. That's the action. And the equal and opposite reaction is that the rocket gets shoved forward. It really is that simple, and it's why rockets actually work even better in the vacuum of space.
Okay, so once we've won that initial battle against gravity, the rules of the game just completely change. The violence of the launch gives way to this quiet and frankly kind of bizarre reality of how things move out there. Welcome to the world of coasting.
And here we meet another one of Newton's greatest hits, inertia. See, down here on Earth, things like friction and air resistance are constantly trying to slow you down. But in the near-perfect vacuum of space, those forces are basically gone. And that is the real secret to deep space travel. It means you don't have to keep your foot on the gas.
And this is what that actually looks like. You have one powerful burn at the beginning to set your speed and direction. And then, the engines go silent, the spacecraft just coasts, traveling for years, sometimes even decades, across millions and millions of kilometers on nothing but pure momentum. It is the most fuel-efficient road trip you can possibly imagine.
Okay, so we know how to go in a straight line. But what about traveling across the entire solar system? That takes a whole different way of thinking. It's less about brute force and more about this incredibly elegant dance with the biggest player in the cosmos: gravity itself.
Right, so here's the problem. Even with all that coasting, trying to get to places like Jupiter or Saturn would take an impossible amount of fuel if we had to do all the work ourselves. So what's the solution? Well, we get the solar system to do the heavy lifting for us. This move, the gravity assist, is seriously one of the most clever tricks in the entire aerospace playbook. By aiming a spacecraft just right, so it flies super close to a planet like Jupiter, we can basically steal a tiny bit of its orbital energy. The planet's massive gravity grabs the spacecraft, whips it around, and then just flings it back out at a much, much higher speed.
It really is the perfect description. It's like getting a free push across the solar system. This is the technique that made those grand tours of missions like Voyager possible. It let them visit multiple planets with just the fuel they launched with. You're literally using a planet as a cosmic slingshot. It's brilliant.
All right, so we're moving incredibly fast, and we're using planets to go even faster. But how do we know where we're going? How do you possibly steer a course when you're crossing billions of kilometers of pure empty space? It's this incredible mix of old school and new school tech. Onboard star trackers, just like ancient sailors, use the fixed positions of distant stars to know exactly where they are. Gyroscopes make sure the craft doesn't start tumbling around. And when a tiny course correction is needed, little thrusters give a gentle puff of gas to nudge the spacecraft onto the right path, often based on commands that were sent from Earth hours ago.
And looking ahead, it gets even cooler. Ion engines are like the marathon runners of space travel. They produce a push that's unbelievably gentle. We're talking about the same force as a piece of paper resting on your hand. But, and this is the key, they can keep that push going for years, slowly but surely accelerating to speeds that conventional rockets could never even dream of.
You know, getting there is only half the battle. Space isn't just empty, it's the most hostile environment we know of. Simply surviving the journey is a monumental feat of engineering.
When you're out there, your spacecraft is under constant attack. You've got invisible streams of high-energy radiation trying to scramble its electronic brain. The temperature can drop to hundreds of degrees below zero in the shade, then spike to scorching hot in the sun. Oh, and a tiny speck of dust, moving faster than a bullet, can punch a hole right through your hull.
So, how do we survive all that? Well, we build our spacecraft like armored tanks. They have layers of special shielding to deflect radiation and coatings to manage those wild temperature swings. We give them autonomous brains, computers that can react to a problem way faster than a signal could ever reach Earth. And for missions with people, we create these tiny, self-contained biospheres that constantly recycle every single drop of water and breath of air.
And that really brings us full circle, doesn't it? Every rocket launch, every orbital maneuver, every single course correction, it's all a direct application of the fundamental laws that govern our universe. We get to explore the cosmos not because our tech is some kind of magic, but because we've learned to understand and, well, speak the language of physics.
So we've learned how to navigate the invisible currents of the cosmos. We've mastered the art of coasting, of falling with style, and of surviving the great void. We understand the rules of the game now. So the only real question left is, where will they take us next?